Hello, welcome to another module in this massive open online course. So, let us continue our discussion on the music algorithm. As you are probably aware by now, music stands for multiple signal classification, which is used to estimate the direction of arrival when you have multiple targets and an antenna array at the receiver, and these multiple targets they are either transmitting their signals or reflecting the signals that are initially transmitted by your radar and so on, right. So, we have music algorithm, which is considered to be one of the path breaking algorithms in array processing, significantly popular for direction of arrival estimation. This is known as multiple signal classification, and we have seen the model for this is you have your vector. If you go back and take a look at it, you have your y1m, y2m, you have your y bar m, which is essentially your a bar theta 1. So, you have your vector which is y bar m, which is the vector of the matrix of DOA vectors. That is, you have your a bar theta 1, a bar theta 2, a bar theta p times x bar m plus your noise vector this is the matrix A of, you can say, of theta, or you can call it as A of theta bar, which is the matrix. You can see this is the matrix which contains the array response vectors corresponding to the DOAs, directions of arrival. So, each of these are your array response vectors, right, array response or array steering vectors, you can also say. For the directions of arrival, right, of the targets. Okay. So, essentially we have y bar of m, which is equal to your y bar of m, which is equal to you can write this as we have seen above, a theta bar into x bar of m plus n bar of m, and now I can estimate the output covariance, right. So, I can evaluate the output covariance, evaluate the output covariance matrix. So, this becomes your expected value of y bar m, y bar Hermitian m, which you can write as a theta bar times expected value of x bar m, x bar Hermitian m times A theta bar plus expected value of n bar m, n bar m, n bar Hermitian m. And the important thing to realize here is that if you look at the matrix A theta bar, right, the matrix A theta bar, it contains p vectors, A theta, A bar theta 1, A bar theta 2, A bar theta 1, theta p. So, this has p columns, therefore, this is of rank p, right, that is the important thing. So, this vector A theta bar, the rank, the important thing is this is of rank equal to p, since it has p columns, only p columns. Okay. So, the rank is not equal to L, but the rank is equal to p. Now, that implies, now let us look at this, I can always write this as A theta bar times R s times this is going to be A theta bar Hermitian, this where this is a p cross p matrix, which is the covariance matrix of the input, plus noise covariance, which is sigma square. Assuming the noise samples are independent identically distributed, noise covariance will simply be sigma square times identity. Important point here is again, once again, this is this A theta bar times R s A bar A theta bar Hermitian. This is a rank p matrix, right, if there are p targets, and therefore, this will only have p non-zero eigenvalues. This is a positive semi-definite matrix, and remember, the number of non-zero eigenvalues is equal to the rank of the matrix. So, therefore, the number of non-zero eigenvalues will be equal to p. Okay. So, therefore, the important thing to note here is this rank, overall rank equal to p, implies the important observation here is the number of non-zero eigenvalues is equal to p, and therefore, I can write this as u, right, u. The eigenvalue decomposition will be, this will be an L cross L matrix U, sigma this will be lambda 1, lambda 2, lambda p, and the rest p minus L minus p eigenvalues will be equal to 0, right, times U Hermitian, plus I can write sigma square identity, I can write as U Hermitian. Now, couple of things over here. First, as we have already said, right, only p non-zero eigenvalues, only p non-zero eigenvalues, and L minus p eigenvalues are equal to 0. L minus p eigenvalues equal to 0. Okay. Now, further, if you look at this eigenvectors, remember the eigenvectors of a positive semi-definite matrix are orthonormal, right. I can find an orthonormal set of eigenvectors. Therefore, the matrix U will be such that U Hermitian equal to U Hermitian U equal to identity, right. So, U is a unitary matrix, right. So, since eigenvectors of PSD matrix, a positive semi-definite matrix, these are orthonormal. So, this implies your U Hermitian U equals U Hermitian equals identity. Therefore, if I look at this R y, which is expected y bar Hermitian, this is your output covariance matrix. If you look at this, therefore, I can write R y, I can now simplify this as u times, I can combine both these things, I can write it as u, right. So, this is basically implies u is a unitary matrix, u is a unitary matrix, okay. And therefore, I can simplify this as u lambda 1 plus sigma square, lambda 2 plus sigma square, so on, lambda p plus sigma square, and the rest will only be sigma square. So, the rest, when you combine these two, the rest L minus p will be sigma square, will be some low value sigma square. So, these are the large, so p large eigenvalues, right, and the rest L minus p are equal to sigma square. So, L minus p eigenvalues that is, if you look at this over here, when you combine these two components, that is the u, this matrix, let us call this matrix as lambda u Hermitian plus sigma square u Hermitian. So, the way we are writing this is, if you look at this, you can write this as R y equals u lambda u Hermitian plus u sigma square identity times u Hermitian. So, this will be equal to u lambda plus sigma square identity times u Hermitian, which is now, if you write this, this will be equal to u, and this matrix lambda plus sigma square times identity, this is essentially your lambda 1 plus sigma square until lambda p plus sigma square, and the rest L minus p identity entries will be sigma square. So, this is essentially your this matrix what we have written over here is essentially your lambda plus sigma square times identity. Okay. And now, if you look at these are the key, right. So, if you look at these L minus p eigenvalues, which are sigma square, now these correspond to the eigenvectors of these correspond to the eigenvectors which correspond to the which correspond to 0 eigenvalues of your matrix A theta bar RS A theta bar Hermitian. Okay, so let me explain. So, this sigma squares, so when you look at these L minus p eigenvalues, these are small, okay, these are small and these are equal to sigma square. And now, where are these arising from? If you go all the way back and if you trace these things, you can divide the eigenvectors into two states, u1 bar, u2 bar, up bar. These eigenvalues are lambda 1, lambda 2 up to lambda p, and u bar p plus 1, u bar p plus 2, u bar L, these L minus p vectors u bar L, these correspond to eigenvalues equal to 0. For the matrix, for, remember, A theta bar R S, which is your source expected value of x bar Hermitian, x m bar Hermitian times A theta bar, right, times A theta bar. Okay. So, these correspond to the eigenvalues of A theta bar. So, u bar p plus, so u bar p plus 1, u bar p plus 2, u bar L, these L minus p eigenvectors, these correspond to, these are essentially the eigenvectors of the matrix A theta bar Rs into A theta bar Hermitian, corresponding to 0 eigenvalues, and therefore, this essentially implies that this u bar p plus 1, u bar p plus 2, so on, u bar L, these belong to the null space, since these are basically eigenvalues corresponding to eigenvalue 0, belong to the null space. This is an important property, these belong to the null space of A theta bar. Implies, this implies, if you take any this implies that essentially if you take A theta bar Hermitian, A Hermitian theta bar times u bar j, this is equal to 0 for j equal to p plus 1 up to L, right. This implies that if you take any vector A bar Hermitian theta I times u bar j, this is equal to 0 for j equal to p plus 1 up to L. This implies that if you take the summation j equal to p plus 1 to L, magnitude A bar Hermitian theta I u bar j whole square, this will be equal to 0 for any theta I which is equal to DOA of, for DOF. So, the interesting point here is that if you take any theta I, which is the direction of arrival of the target of one of the targets I equal to 1 to p, I equal to 1 to up to p, then that must satisfy this equation, that is summation j equal to p plus 1 to L magnitude A bar Hermitian theta I u bar j, the magnitude square of that summation magnitude square of that must be equal to 0, which implies that for any theta I, which implies for where I equal to 1 2 up to p, which implies if I look at the reciprocal of this, that is if I look at this quantity, that is the summation j equal to p plus 1 to L summation magnitude A bar Hermitian theta I u bar square, since the denominator is small, this quantity is going to be very large, right. Since the denominator is 0, this quantity is tends to infinity. implies this quantity is very large essentially. Therefore, how do you now determine the directions of arrival theta? Very simple, plot this function f of theta, call this as a function f of theta, plot it as a function of theta. When that theta equal to theta I, this will be equal to 0, and therefore, right, I mean this the denominator will be equal to close to 0, therefore, the overall quantity which is the reciprocal of this will be very high, right, tending towards infinity, and therefore, you will have peaks in this spectrum, and those peaks will correspond to the directions of arrival, right. So, basically call this as your f of theta, okay. Call this as your f of theta, which is equal to 1 over your, which is basically your 1 over summation j equal to p plus 1 to L magnitude A theta bar Hermitian A bar Hermitian theta times u bar j whole square. So, plot this as a function of theta, plot f of theta. Now, the final step is plot f of theta as a function of theta, plot of f of theta as plot f of theta as a function of theta, and where you have the peaks, right. So, these are your axes, plot this as a function of theta, and your peaks right. So, this peak will correspond to, this will be your theta 1, this will be your theta 2, so on and so forth, this will be your theta p. So, the peaks correspond to, so the peaks and these are your DOA of the, and these are the DOA of the P targets. So, essentially what you are doing is, very interestingly, you are estimating the output covariance. From that output covariance, you are looking at the eigenvectors which essentially correspond to the smallest eigenvalues, which are essentially sigma square. These correspond to the, and the important property is these eigenvectors correspond to the, are in the null space of A theta bar, which essentially comprises of the angles of arrival of your, this corresponds to the angles of arrival of your which corresponds to the angles of arrival of the P targets, and therefore, we construct this cost function f of theta, plot it, the peaks essentially correspond to your angles of arrival of the targets. So, that is the interesting property, and this is how the music algorithm operates. So, you construct, you estimate output covariance, from that extract the eigenvectors corresponding to the smallest eigenvalues, construct this function f of theta, plot the spectrum, right, plot the spectrum, and the peaks, from the peaks you can essentially find out where the targets are present. So, it is a very fast, simple and efficient algorithm, as I have already told you, is one of the most considered a breakthrough algorithm and one of the most popular algorithms for direction of arrival estimation, and this is yet another very interesting and exciting application of the principles of linear algebra, eigenvectors, eigenvalues and so on in signal processing, direction of arrival estimation, which can have so many applications. So, let us stop this module here. and let us continue looking at other aspects in the subsequent modules. Thank you very much.